Say what?
The direction when it's computing the boundary map, the direction counts somehow.
Well, the order. I mean, when we talk about simplexes, we always have to keep the order of the points. So it gives you the boundary, gives you a simplex. The boundary should give you a simplex with a particular order of points. The order is determined by just removing. I mean, you have the order of vertices in the original simplex. You just remove a point, and then you get an order at subsimplex. I mean, the subsimplex is also with the corresponding order of vertices.
Okay.
So, for example, in particular for an edge, the orientation is the order of 2 points. So you can see it counts, it matters.
Okay.
So let me briefly remind you. So in the last lecture, so we considered X, and then we consider X to be a topological space. And so for such topological space, we associated an abelian group Cn. So explicitly, we can write explicitly the dependence on the topological space Cn of X, which is a free abelian group generated by all continuous maps from n-dimensional simplex to X. So such maps can be, so they are usually referred to as singular simplices. In X. So this is because we don't have a so the image of this simplex can be quite weird because we don't have any condition that the map is injective or anything like that. In particular, for example, you can map a kind of a tetrahedron to some sort of, to just, for example, an interval. That's why this in X. That's why kind of these maps can be referred to as singular simplices inside X. Well, this is just terminology. So, so the other terminology is the following. So the arbitrary element of such space is, of course, so by definition, can be written as an arbitrary linear combination of maps, where the coefficients are integers, and such elements are referred as chains. Called chains. Elements of Cn of X are chains. And moreover, if so, let's say we have some chain beta in X. So if so, we also define the boundary homomorphism from Cn of X to Cn plus 1 of X. And so if so we say if dn of B is 0, then B is called cycle, and if B is dn plus 1 of some other chain gamma, then B is called boundary. And then we defined, so we showed there is the following property that the composition of dn is dn plus plus is 0. So we showed this for the case of simplicial homology, but the proof is analogous is completely analogous for dn acting on Cn. And therefore we can define simplicial homology of X as kernel of dn divided by image of dn plus 1. Or using this this terminology, you can say that this is all cycles. We consider all cycles divided. So to be, if you want to specify the n here, we can consider this n cycle, and this will be n bounded. So this is all n cycles modular n boundaries.
But in this case, isn't it the singular homology? Because we are talking about...
Oh, sorry, yes, what I want. This is simple. So what I meant is the proof as in proof is the same. This thing the same as for simplicial. So the main difference between singular homology and simplicial homology is that for singular homology you consider all the Cn generated by all maps, from all continuous maps from synthesis threads, and for simplicial homology this was just a particular set of maps. But it's for the proof of this condition it doesn't matter. So now, unlike in the case of simplicial homology, so again, these spaces are quite, so the Cn is now infinite dimensional space, with the space of all continuous maps. So in general, it will be infinite dimensional spaces. And it's quite hard to explicitly calculate this, but the approach is to actually just to show, the calculation usually to kind of show particular properties of these homologies, and you just use these properties to do the calculation. So let me. So what is the, for example, what is the easiest, the most basic properties which you can show, which you can immediately show? So let, for example, show the following proposition. So let X to be the disjoint union of X alphas, where X alphas are path connected components of X. So any topological space can be decomposed as a disjoint union of its path connected components. And then the statement which you want to show is that the nth singular homology of X is the direct sum of n singular homology of these subspaces. So first, one can see that so if we consider a map from sigma from delta n to X, so since the n-dimensional simplex is path connected, then its image of this map sigma belongs to a certain path connected component. therefore, so if you consider Cn of x, which is the abelian group generated by all continuous maps from delta m to x, we can always each generator belongs to a particular the image of each generator belongs to a particular x alpha. So therefore, we can this abelian group can be decomposed as direct sum of abelian groups corresponding to each path connected component. Right? Because the arbitrary element of this term, so each sigma I we can put in one of these guys. That's why the thing splits into direct sum. And moreover, if we consider the boundary homomorphism restricted to subgroup Cn x alpha, its image will be obviously in Cn plus 1 x alpha. So this just follows from definition of the boundary homomorphism. So we take a linear, when we take a boundary, when we consider boundary homomorphism max not sigma, we take a certain linear combinations, which coefficients are plus minus signs, of restriction of sigma on faces of delta. But if delta maps to a particular x alpha, of course its faces will map to the same x alpha. So we get this property, and therefore, so since so the Hn of x is called by the kernel of delta n, which acts on the space divided by the image of delta n plus 1, acting on Cn plus 1. So since all deals they act independently, they don't mix up these subgroups, we get that for this quotient we also have direct sum decomposition. Questions?
The image of sigma n is belong to Cn minus 1.
Image of
More, yeah.
sorry, yes, it's minus. Yes. This was the question. So another basic property which is to show that if suppose x is non-empty and x is path connected, then the zeroth singular homology group of x is isomorphic to z. How do we prove this? So let me consider the following denoted by epsilon to be mapped from C0 of x to z. Okay, so x is non-empty, therefore it follows that that this epsilon is surjective. This is because if X is non-empty, they are non-trivial. They are of course non-trivial maps. And so yeah, forgot to define. So the epsilon explicitly is defined like this. So if you take an arbitrary linear combination of map sigma I, so each sigma I is a map from delta 0 to X. If you take this some arbitrary linear combination, the map, the result of the map gives the sum of some of the coefficients. And so if X is non-empty, this map is surjective because, of course, there exists at least one map like this, and we can always take it with some integer coefficient to get any integer number here. So once we have this surjective map, so since it's surjective by the main theorem of algebra, we can state that Z is isomorphic to C0 of X divided by the kernel of this map, right? Because the image of any homomorphism is isomorphic to a quotient of the space with Pshitax over its divided by its kernel. Okay, so now we want to show that kernel of map epsilon is the same as image of D1. D1 acts from the boundary map, which acts from C1 of X to C0 of X. So how do we show it? So let's split the statement into two statements. First, let me show that the kernel of epsilon contains image of delta 1. So for this, let me consider the so let me consider arbitrary element. So let me consider some sigma and action of D1 on this sigma, and then first action of epsilon. And so in order to show this, we need to show that this is 0 for arbitrary sigma. So let us see. So sigma here is map from, so it's an element of C1 of X, so this is a map from delta 1 to X. So let me denote the vertices of delta 1, which is the one simplex is B0, B1. So by definition of delta 1, this will be sigma restricted to B1 minus sigma restricted to B0. So this is a 0 simplices. B1 and B0, these vectors B1 and B0. And but of course, since epsilon acts by just taking the sum of the coefficients, this will be 1 minus 1 as a result of epsilon, which is 0. So this shows that image of delta 1 is inside the kernel of epsilon. Now we want to show the opposite. The kernel of epsilon belongs to image of D1. So let us take some element in the kernel of epsilon. So let us take some linear combination of sigma i's, where now sigma i's maps from delta 0 to X, such that epsilon sink is 0. But epsilon of the sink is by definition the sum of coefficients. So if this sum, this means that this sum belongs to kernel of epsilon, if and only if the sum of the coefficients is 0. So now we want to show that the sum, such sum is when the coefficients sum up to 0 belongs to image of D1. So sigma i's, so the sigma i's are maps from zero-dimensional simplices to X, and of course they are completely, so since the zero-dimensional simplex is homomorphic to a point, this means the sigma I is completely determined. They're completely determined by the image of this point, which is a point in X. Now we want to use the fact that X is path connected. And more or less us fix a certain base points in X, X0. And so from the fact that it's path connected, it follows there exist maps which are paths from passes in X, which are maps from the unit interval to X, such that Ti restricted to 0 is X0, and Ti restricted to 1 to the end is sigma I of delta 0. But of course we can consider the interval as a one-dimensional simplex, right? And then this means that so in other cases, so what? To be more precise, sorry. What I mean here is the image, the value means essentially the same thing, but Ti of 0 is X0 and Ty of 1 is sigma I of delta. But in other, this can be recognized as the restriction of this map to V0, which is identified with 0, is the same as singular simplex sigma 0, which is a map. So it's a map from delta 0 to X, such that it maps. Let's see. So this is just a point. The point here is mapped to X0, and the restriction of Ti to V1 is sigma. So this is just a reformulation of the condition that the beginning of the path is X0 and the end of the path is the image of delta 0, which is a point under the action of sigma I. So if you want to consider this path as a singular one simplex, because the interval is one simplex, this means that the restriction of this map to the end is sigma 0, and to the from to the start of the interval is sigma 0, and to the end it's sigma I. In particular, it follows from the definition of D1, it follows that the D1 of Ti is sigma I minus sigma 0. follows from definition of the boundary. And then, if you take d1 of the sum of mi, ti, then this gives some bilinearity, and gives this minus this. But of course, this is 0, because the sum of the coefficients is 0. Sum of ni's is 0. So this shows that this is indeed this guy belongs to the image. So since we found one chain, that the d1 of it gives us this element. So indeed we showed this property. So we took an arbitrary element in the kernel of epsilon and we showed that it's actually d1 of something.
Excuse me, but why is it 0? Because here we have sigma 0, not only the coefficient.
Yeah, but this is just an overall. The sigma 0 is the same for any I, right?
Ah.
So we can just take
Okay.
take the sum, take the sum of the coefficients. So we showed that the kernel, finally we showed, so combining I and I, 1 and 2, we showed that indeed they're the same. And since, so H0 of x is, so by definition is the kernel of d0 divided by the image of d0 of d1. But so d0 acts trivially on c0 of x, so we can just replace it by the whole space. And then using the statement which we just proved, we can replace the image of d1 by the kernel of epsilon. And then, before we showed that this is isomorphic to z in the very beginning of the proof. So this ends the proof of the proposition. Any questions? Particularly from these two propositions, you can make the following corollary. So if X is the joint union of path connected components, then the zeros homology group of X is the direct sum of copies of Z.
I'm just curious, why kernel of the boundary map 0, number 0 is C, not A?
Well, because how do we have this? How does the boundary map work? So we have, for example, if you start C2, D2 acts gives C1, then we get act D1, C0 of X, but then D0 there is nothing after that. So by definition, it's just okay. So the kernel is also. Any other questions?
Sorry, I didn't understand, but the boundary map acts injectively or subjectively? No, it doesn't depend.
No, it can act whatever. I mean, just some homomorphism. I mean, in general, it has a non-trivial kernel, both kernel and image, they're non-trivial. But of course, in the special case of D0, it just maps the whole thing to 0, so the kernel is the whole system. So let us compute the homology for very single homology for a very simple case, but in a sense it's actually kind of important result. So the nth singular homology of a point is equal to z when n equals 0 and 0 otherwise. So since our topological space is a point, for any n, there exists a unique map sigma n, which will be denoted by sigma, which will be denoted by index n, from delta n to a point, right? Because there is a unique map to a point. Everything maps to the same point. So in particular, it follows that the Cn of a point in this case is so it's generated by just a single map. So it's isomorphic to that. There's the single generator. So how does the boundary homomorphism act? So if we consider Dn, so there are only one generator, so we just need to, as action of the boundary map on this generator. So by definition, we have the following sum from 0 to n, minus 1 to the I, and then we want to put a restriction of sigma n to a particular phase. But since there is only one, again for n minus 1, simply there also will be just a unique map. So for any term in the sum, we have the restriction of sigma n to its phase will be sigma n minus 1. And so the result, so since we can again combine the coefficients, and the result will be it's sigma n minus 1 when n is even. There will be one term. In the sum, there will be one. The sum will be 1 if n is even. And it will be the sum will be 0 when n is odd. Right. So the singular chain complex. So in this case, so in general, this by singular chain complex we mean, as we saw before, we mean the following sequence. Is in this case, it explicitly looks like this. So let me write it from the beginning. This will be Z, which is C0. This will be another Z, which is C1. There will be another Z, which is C2. So of course this is map is 0, but then we showed that the map from, so D1 acts as, so it takes, so D1, so for D1 acts, and is even, so it acts as a so let me see. So
Identity?
Sorry, something is.
For the n evens, it is just the identity, and for the odd, it is the trivial.
Yes. But so here it should be. So here it should be. So it should be 0. It should be negative. So in particular, so H0 is so the kernel will be the kernel will be the whole again the whole C0, and the image is trivial. Right? So this will be the whole Z. Then for n odd, Hm will be so the kernel. So in general, it's kernel of Dn divided by the image of Dn plus 1. So when n is odd, the n is trivial, so the kernel will be the whole Z. And so when n is odd, n plus 1 is even. So in this case, Dn plus 1 will be identity. So the image will be also the whole Z. So this is trivial map and this is identity. So the quotient will be 0. And when n is even, again, so now Dn will be identity, so the kernel will be trivial. But Dn plus 1 will be a trivial map. So the image also will be trivial. So this is the case when n is greater. So this shows. So this H0 component. So this says proves the privilege. Questions? So now let me introduce the following notion, which you later need, but we won't need it right now, but you will need it to solve to approach one of the exercises. So a sequence of homomorphisms let's say a n plus 1, a n, a minus 1. So this is the homomorphism, let's say alpha n plus 1, alpha n plus 2, alpha n plus 1 between groups an is called exact if and only if the kernel of alpha n is the same as the image of alpha n plus 1 for any n. In particular, we can make this formula. So if chain complex is an exact sequence, then the corresponding homology is trivial, right? Because the quotient of kernel divided by image will know. So the other definition, so there is a special important case of exact sequences which are called a short exact sequence. So a sequence is an exact sequence of the form where the only 3 non-trivial groups and they start with 0 and end with 0, is called short. So let me give you some example. So I can see the one sequence of Z, and then say Z2, where the first map is given by multiplication by 2, and the second map is given by reduction modulo 2. So if we take an integer here, we map it to 2m, and if you take some integer here, we map it to m mod 2. And of course you can see that the image, the kernel of this map is exactly the image of the previous. So we will need this. This is important, very important notion for homology, which we will later use. But before, so let me introduce another definition. So we want to consider, so again, we want to study some properties. What we define homology, we showed some, like what is the homological in some basic cases. Now we want to show some other properties of homology. So let F to be mapped from topological space S X to topological space Y. Again, we always consider maps to be continuous. Then there is induced map between the corresponding chain complexes, which acts on Cn of X and gives an element of Cn of Y. And it's defined such that so if you have so the elements here, they're generated by so the arbitrary element here is of the following form. It's a linear combination of maps sigma I from delta m to x, and we want to map it, this linear combination, to a linear combination with the same coefficients, where each sigma I we replace with the composition of with the map f. Right. So now this will be a map from delta m to y. So this is gives a well-defined map from Cn of x to Cn of y. Right. So the map between Cn's corresponding to map f is denoted by f sharp, is index sharp. So this induced map has an important property, which can be formulated as follows. So for x, we have a singular chain complex, so the sequence of boundary homomorphism between Cn's. So very often people, I mean, when it's clear how the boundary homomorphism acts, very often people, and this is what we do, they suppress the explicit index and just write D. And then we have the same thing for y. Again, we can heavily overuse this notation D, but of course all these maps they're different because they're between different abelian groups. And then we have the induced maps F sharp here, F sharp here, F sharp. So. And the statement is this diagram is commutative. Therefore it doesn't. So if we take an element here and we act it by D and then by F sharp, this gives us some element here, but we can also bring it first here and then here, it will get the same. So again, to show this, so let us take some arbitrary, so some generator of this abelian group, so some map from. Well, let me show commutativity here. It doesn't matter because it's just a shifted by index. So let me show the commutativity of this square. So let me take a map.
Like a small typo of the second sequence. Also, it should be minus 1.
Yeah, yes. So let me take a generator of this group, some generator of this group. So it's a map from delta m to x. So again, we can fix the notations for this simplex. So its vertices are b0, bm, and then so we want to consider how F sharp acts on D of sigma. So we took a generator here and we acted first by D and then by F sharp. So first we use the definition of D, the boundary homomorphism. So this is the following sum. So we take sigma restricted to some simplex where we remove is vertex. So then by linearity of the induced map, so we just act by F sharp on this guy here. So this is the composition of F, the sigma restricted to this subsyntax.
But we can exchange the restriction with the composition.
Yes, exactly. So we can, of course, yeah, we can instead of taking first restriction and composition, we can, this is the same, and taking first composition and then restricting. And this is by definition, this is a D of, so this is by definition F. So the thing in the parentheses is the F sharp of sigma, and the whole thing is the same as D of F sharp. So this proves the proposition. So you can exchange D, the boundary homomorphism is F sharp. So again, let me remind you that also this D here, this D has the same notation, the same letter, such it denotes the different maps, right? So in the first case, it's a map, this map, and in the second case, it's this map. So now, so we show that the homomorphism, the continuous map between the positive space X and Y, it induces a map F sharp, which is denoted by F sharp between the corresponding chain complexes. which has this nice property, and this nice property can be used to show that there is the following well-defined map between induced map between the homologies themselves. So let F again be the map from X to Y. Then the push forward induces push forward map, which is denoted by F star, the same as the same notation as was for fundamental group. So it's defined for any n, and takes Hn of x to Hn of y. So the push forward homomorphism between abelian groups Hn of x and Hn of y. And it's defined as follows. So if you take, so by definition, this is the kernel of dn divided by the image, so image of dn plus 1. So here, let me explicitly denote that by x, symbol x, index x, that it's acts on the chain complexity corresponding to space x. And this guy is the same thing but for y. So therefore, so the element in Hn of x can be represented with equivalence class of, let's say, some element beta, such that where beta is in the kernel of x. The equivalence class modular the addition of an element from the image of dn plus 1 of x. And we take it, so since this is the kernel is a subspace of Cn of x, we can act on beta using the map F sharp. So of course we want to show, as usual, for maps between some portions, we want to show this actually well defined.
There is just a typo that it should be image in the homology of
Oh, yes. So well defined. So first we want to, so in general, we know, so the map F sharp, it gives us some element Cn of y. But we want this element to be actually the element of the kernel. So, so first we want to check that d and y of F sharp of beta is 0. And this is indeed, so now we use the property that we can exchange d and F sharp. So this is from the proposition above, so this is the same as F sharp d m x beta, and since this is 0 and this is a homomorphism, this is 0 because beta is insecure. And so the second part of well-definedness is that if it, so we can take a different representative of beta, different representative of the homology class. So we suppose we take, instead of beta, we take beta plus some element of the image of the boundary homomorphism. Say gamma. So this is the only freedom we should have. So now this guy, so if you take instead the class corresponding, so if you use the definition of this map, this should give us F sharp of beta plus dx n plus 1 gamma. Then by linearity is the same as f sharp of beta plus f sharp of this guy. But this is again, we can again use the property of the proposition of exchange d with f sharp. So this is the same as dn plus 1 y f sharp of. But this is indeed in the same class as f sharp indeed, because this is belongs to the image of the d here. So indeed, as a class, we get the same class in the homology. Questions? So it has so induced the push forward has a similar nice property as we had for push forward for fundamental group. In particular, so if suppose we have map f from x to y and map g from y to z, then take first the composition and take its push forward, the same as composition of push forward homework. And the second property is that so if you have identity acts on x, and we consider its push forward, it will be identity acting on identity homomorphism acting on HN of x. So this is these properties are more or less obvious. Question?
The order of the compositions.
Oh, right, yes. Okay, this is so. This follows more or less from definition. This is because so if you take some sigma in delta, which is a map from delta n of x, so we know that we can first, if you want to algebraic composition of this map on sigma, we can the same as first. So what I mean, we can do this the composition in this order instead, right? And then from the definition of the induced map, we have told us the f sharp, the sharp of the composition of f and g is the same as f sharp composed with g sharp by this definition of the induced map. And of course, since the push forward is just given by the action of the induced map on the chain complex, we get again from the definition of f sharp and this is the definition of f star. We immediately get the star composition is the same as composition star. So the second part is actually the same. So if you take so the composition of the identity with the map sigma is the same as sigma. So it follows that the induced map is identity on Cn of x, and then it immediately follows the push forward. Push forward is defined directly through this induced map is the same as identity on the chain of x. Questions?
Can one say that for the second part that if we take identity and compose it with itself, we get the identity, and if we apply the push forward, we get the push forward. The square of the push forward is the push forward itself, and since the group morphisms of the homology group is itself a group, since therefore we get an idempotent in a group, and therefore it must be the identity. I mean, just using the first part without using the definition.
Well,
because we just here having that the homomorphism from the homology group of X to the homology group of X, it is itself a group.
well, you want to show that. Well, I'm not sure because this can be. You can end up with having some idempotence.
Yeah, but we are in a group.
on the abelian group.
Yes, but the only idempotent is the only element in any group such that it's square itself is a identity, because we can just multiply by the elements.
Oh, but we can. So why? Here we don't have we don't know that there is inverse on this one. It can be something like a projection. I mean, so we can use. I mean, if you have these two properties, then you can show that the inverse, the push forward of the inverse is inverse. Or you can, if you showed it before, then indeed you don't need this. So you only need this kind of two conditions to show the third. Any other questions? The other important property, so which you want to show that if let us have two maps from X to Y, and suppose they are homotopic. Then we want to show that the corresponding push forwards are the same maps. Between the corresponding homology groups. So this will actually require some work. So see, they are homotopic. This means that there is homotopy, that is a map from X times unit interval to Y, such that F restricted to 0 is the same as F, and F restricted to 1 is the same as G. And so let me consider, so instead of X, let me consider X times interval. Let me for a moment consider simplex times interval. still consider the simplex times the beginning of the interval. So this is, of course, this can be identified with n simplex itself. And let me choose the notations for the vertices of this n simplex to be v0 and vn. And delta n times the end of the interval gives another copy of the simplex. Now let me use, so in order to distinguish it, let me denote the corresponding vertices to w0 to wn. And we also want to, so in particular, we want to order to be consistent so that so if you consider, so if P is a projection, so the map from delta n times interval to delta n is a projection on the first factor here, so that projection, the P of Wi is the same as P of Vi is the same as P of W. So geometrically it means, for example, let me draw a picture when n equals 2. So we have, so this space looks something like this. So we have a simplex here, which is vertices. So at the top we will have vertices W0, W1, W2. Here we will have vertices V0, V1, V2, and we can see the product of the simplex times the unit interval. So this is delta 2 times 0. So let me notice that delta m times interval, so the whole thing can be represented as a union, of n plus 1 simplices with the following vertices. So we start with V0, go till Vi, but then we continue with Wi, and then we end with Wn. And they have non-intersecting interiors. So what is happening in this example? So so in this example we have first so if I is equal so let me start with V0, so V0, W0, W1, W2, so this example when n equals 2, and this would be simplex, so let me zone by red, this would be simplex, how does it look? Looks like this. And something like V0, V1, W1, W2, and so this is this age. And this simplex, and then finally there will be V0, V1, V2, and W2. And this will be this guy. So we split this kind of triangle times interval into 3 tetrahedra with non-intersecting interiors. So this is an example when I equals 2, but of course the general situation. Okay. Now we want to we can define what is called prism operator. So this will be operator which given by P acts from Cn of x to Cn plus 1 y. Let me take some generator here. So this is a map from delta n to x. So delta n, I will say that this has vertices 0, Vn. And the result, so this sigma is mapped to the following sum. The sum over I minus 1 to the I. And then I take a composition of F with sigma times identity acting on the interval. And then I will restrict this to one of the simplices, M+1 simplices as here. 0, I, Wi, and so on till Wn. This is probably not very good, but this is exactly the same as. So let me elaborate a bit on this. So if I consider, so of course if I have so I can consider map from delta n times interval, which is sigma times sigma which acts here, and identity which acts here to x. So sigma brings delta n to x, and identity brings interval to itself. And then I can argue by f, big F, to go to y. So this is why this composition is well defined. So it gives a map from this composition gives a map from delta n times interval to y. And since this guy I could decompose, there are some subsimplices of this form, of this type. I can restrict this map, the composition, to one of them, right? And then I take it with certain coefficient plus minus. Is it clear how the right hand side? So it looks very similar to the delta map, but it's not the same. In particular, it increases the degree here from n to n+1. And we want to show the following property, that the composition of D with P, so this is what we want to show, is the same as.
But excuse me, what just the dimension increases by what?
Yes, so n goes by n+1. So this index is often called a degree.
Yeah, I mean, like in definition, from which part does we see that it increases by one?
So this was n. So this was n simplex,
Yes.
and this was n plus 1 simplex. So we started. So for example, here we started with 2 simplex, which was triangle, and then we consider this kind of the product, and we split it into 3 simplices. And here we get we end up with a linear combination of maps from these 3 simplices. So we started with 2 simplex and ended up with maps from 3 simplices. So we want to show this property. This property is a relation on the homomorphisms from let's see, from Cn of x to Cn. We want to show this. So it's usual to just show it on an arbitrary generator. So let me consider the action of the left-hand side on some sigma. So we know how p acts on sigma, we already wrote it down. Now we want to act it by the boundary homomorphism. So there will be an extra index, extra sum over j. And so we want, as usual, when we act by a boundary map, we want to start removing vertices here, right? And so it's convenient to split a sum first when G is, when we remove vertices from, so okay, let me, so it's not very clear, let me actually rewrite this so it's more visible. So this is a restriction to also from P0 to VI, then VW, WI, to W. So first, when let's say J goes below up to I, and so in this first term we will remove indices in this part, V indices, V vertices. So it will looks the term will looks like this: -1 to J, -1 to I, and so F. So we essentially repeat the whole thing, sigma times identity, and then we restrict it to B0. So we remove J's vertex, and then continue. As before. And then there will be certain, the second term, where G runs from E, starting from E. So we will remove, which means we will start removing vertices, it's doubly vertices. So again, we start with I and go up to N. So we jump since we we repeat it. So for index I here in this term and index I here, they actually correspond to neighbor to different vertices. So we actually we want to increase this index here. We want to shift the index here by 1. So we get an extra minus. So here we keep all V vertices up to I, and we remove J's W vertex. Now the whole thing, we want to recombine into 2 terms. First, let me know term, the part A, so this will be all terms in these 2 double sums, such that terms with I equals J. And the second part will be, should be known by B, will be terms with I is not the same as G. Okay, so let me consider the part A. So the terms with j equals I would be, first consider terms with j equals I here. So, so if I restrict my j to the I, so I get just sum over I. So this minus 1 will be the same, so it will be just plus 1. Sigma times identity composed with F. And then, since j equals the same as I will have my vertices will be the following. So let's go start from V0, go till V. Let's see. So j equals I, so I remove this, so I have I minus 1. And then I continue with Wi up to W. And from the second double sum, I will have, so here when f of j equals to I, this will be actually minus 1, sum of I, f sigma times identity. And then, so here again, j is the same as I, so this will look like V0 till Vi, and then I start with I plus 1. Go to V. But now we see that this is actually the same as this, just I is shifted by 1. Right? So almost all terms here will cancel. There will be only term here is index when I equals 0, which will be not paired up with any term here. And there will be last term in this sum, which will not pair up with anything from here. So almost everything cancels except the F0 sigma times identity restricted to so this is the first term here will be when everything is W. Minus, and here the only survivor will be when everything is D. But of course, so we can restrict, so this restriction of sigma times, so this subsimplex is essentially is a simplex, is a subsimplex at the end of the interval on which this identity acts. So this is the same as, exactly the same as f composed with f restricted to 1 composed with sigma. And the same thing will be here. So this is a subsimplex at the beginning of the interval. So this V is so the V simplex is in the beginning, and W simplex is the simplex at the end. So the F restricted, the same as F restricted to 0, composed with sigma. And this is the same as, by definition, so this is, since F is a homology between F and G, this will be G composed with sigma minus F composed with sigma. Or the same as G sharp of sigma minus F sharp. Okay, so well, I guess so. It's time as well. Well, we almost at the end of the proof. but okay, no, maybe it's not. Yeah, maybe it's not enough time to. Okay, so let me. So the part. Let me continue in the next. Because the next calculation is also rather lengthy. It will require.